So this last column on your periodic table is called the noble gases. I'm going to just outline them so that we can identify it. And then we'll write the word noble gases. And these are called the noble gases because they are already stable. And so what that translates to is that they have a full valence shell. Each one of them does. The reason that they're here at the end of your periodic table, or at the end of each row, is because that the S and the P sublevels are both full already. So if we go back to this part, talking about having a full valence shell, which is your outer S and P sublevels, every single time you have a noble gas, it has to be full because your S sublevel would have 2 before you get to this one, and all of these would end in P6. Except for helium, which ends in S2, but that's a different thing. So if your noble gases all have an electron configuration that ends in P6 at that specific energy level, so if we take neon, for example, we'll skip helium since that one's kind of a weird one. If we start with neon, neon's electron configuration would end with 2s2, 2p6. And then argon's electron configuration would end with 3s2, 3p6. And krypton's electron configuration would end with 4s2, 4p6. And xenon's would end with 5s2, 5p6. We skipped the D block because the D block isn't a valence shell, so it still can have higher energy, but it's not ever going to be your outermost shell, and that has to do with the shapes of these with the quantum mechanics model, so you don't have to worry about that. What you do need to understand is that for the most part, or for all of these noble gases, they have a total of 8 valence electrons, and that comes from the 2 in the S sublevel and the 6 in the P sublevel at each of those energy levels. Helium is still a noble gas. It still has a full valence shell, but it only has the S sublevel, which is why it's full with 2. So helium has 2 valence electrons. Sorry, 2 VE right there. But then neon, argon, krypton, xenon, and radon, and then this one, I don't know anything about this guy. But these guys all have 8 valence electrons. I'm going to assume this one also does, but I'm not going to attempt to pronounce it. So each of these have 8 valence electrons, and where that comes from is the combination of their S and their P sublevels at their highest energy level. So when we talk about valence electrons, all of our elements are trying to end up looking like the noble gases. Does that make sense? Yes, no? Okay. So 8 valence electrons for the majority of them. If we take this one step backwards, just like how all of the noble gases would end in P6, if I go here, all of these in this column would end with what in their electron configuration?
INE.
Okay, name-wise, yes. But when we talk about electron configuration, like 1s2, 2s2, 2p6, if we go not to P6, but here, what would these end in? P5. So fluorine would be 2p5. This would be 3p5, 4p5, 5p5, 6p5, 7p5. Which means that they have 1 less valence electron. It's going to be 2 plus 5, which gives me a total of 7 valence electrons. So this entire column has 7 valence electrons. This column here would all end in P4, right? So if I'm counting 1, 2, 3, 4, so this would all end in P4, 2P4, 3P4, 4P4, 5P4, 6P4, 7P4. So the P4 plus the S sublevel at each of those, so 2 plus 4 would give us how many valence electrons? 6. So are you noticing the pattern? Here we have P3, so P3 plus the 2 would give us 5 valence electrons. This whole group would have 4 valence electrons. This whole group would have 3 valence electrons. We skip all of the D block because these have varying numbers of valence electrons. That's why we don't count them when we're counting valence electrons. And then our group 2 here, it would end in S2. So S2 would have 2 valence electrons. And then here, S1 would have just 1 valence electron. So it goes in order. You have 1 valence electron, 2 valence electrons, skip the entire D block, and then pick it back up. 3, 4, 5, 6, 7, and then pretty much 8 valence electrons. So if you label this, I would label 8 up there, just keeping in mind that helium, remember we move helium over here. So helium's kind of our weirdo. And then the other set of numbers that we generally will label on our periodic tables is what we call oxidation numbers. I'm going to write that word. Your oxidation number is just your charge. So it sounds confusing, it sounds difficult, and it sounds scientific, but really your oxidation number is something that we've already been talking about. So this little charge that's on here, the +1 or +1 or -3 or -2, that is your oxidation number. And so that has everything to do with the number of valence electrons you have. So when we do oxidation numbers, it follows the same pattern as the valence electrons depending on what that atom would do. So when we have just 1 valence electron, so this is like the sodium and the lithium example that we did, when you have just 1 valence electron, it's easier to lose your 1 valence electron and drop down to a lower energy level. And when you lose that 1, you become more positive, so it has a +1 charge. On the opposite side of this, if you have 7 valence electrons, you are really close to having 8 valence electrons. So instead of losing all 7 of your valence electrons, you're going to just gain 1 electron to have 8 and become more stable. So you would have a -1 charge because you gained an electron that has a negative charge. If you have 6 valence electrons, you're not going to lose all 6 of them. You're going to gain 2 instead, since that's easier. And if you gain 2 electrons, you have a -2 charge. I'm skipping around. If I have just 2 valence electrons, it's easier to lose 2 than it is to gain 6 to reach 8. So this one's going to lose 2 electrons, which would leave it with a +2 charge. Then if I have 5 valence electrons, what's easier, losing all 5 or gaining 3 to reach 8? Gaining 3, so if you gain 3 negative things, you're going to have a -3 charge. If I have 3 valence electrons, I can either lose those 3, or I can gain 5. So what's it going to do? Lose 3. So my positives will outnumber my negatives by 3. So I would have a +3 charge. And then the weird one is 4 valence electrons in the middle. If I have 4 valence electrons, it is equally as easy to gain 4 as it is to lose 4. So this is going to depend on where those electrons are coming from, or going to basically which element that thing is bonding with. So this one can do both. It's either going to be a +4 or a -4 charge. And since the goal is to become stable, it's to look like one of these noble gases, the noble gases themselves don't have an oxidation number because they don't want to gain or lose any electrons. I'm going to zoom that out so you can see the full picture. So your valence electrons go in order. We have 1, 2, skip a few, 3, 4, 5, 6, 7, 8. And then our oxidation numbers follow the same rules that we were practicing with this, whether you're going to gain or lose, whatever. But if we look at it as a whole, we have +1, +2, +3. And then going the other way, we have -1, -2, -3 until we get to 4, and then that one can do either one.